Hello everyone and welcome to Chapter 7. Alkyl halides are the functional group that we will be focusing on in this chapter, and what they do in reactions is nucleophilic substitution and elimination reactions. Let's get started. As an introduction to just what an alkyl halide functional group is, if we remember from previous chapters, an alkyl halide is a carbon attached to a halogen. For our case, that halogen will be chlorine, bromine, or iodine. Fluorine is not great at these reactions because what the halogen will be doing is being our leaving group in all of these reactions. Fluorine is not a good leaving group. We'll talk about how to identify leaving groups in a little bit, but right now what we would want to be able to say is each highlighted carbon here has a different hybridization, either sp3 or sp2. What I just want to present here is that each of them represent a carbon to halogen bond, but the alkyl halide that we are going to be looking at in this chapter is sp3 carbons to halogens. Those are our definition of what an alkyl halide actually is. And so those are the ones that will be undergoing our reactions today. Now, as we dive into substitution and elimination, which alkyl halides undergo, we just want to see a generic route here. So no curved arrows yet. We'll get to the curved arrows in just a little bit, but alkyl halides can undergo a substitution reaction when reacted with a nucleophile. So we learned the term nucleophile is something that is nucleus loving. It has extra electrons. It is looking for the electrophile. So in both cases here, our electrophile will be our alkyl halide. Specifically, why is it an alkyl halide? And we'll dive into this a little bit more, but that bond between the carbon, the sp3 carbon, and the halogen is polar. The halogen is typically more electronegative, so therefore the delta minus, and the carbon, more electropositive, is the delta plus. And that's why when we look at these carbons, they are the electrophilic center. Now for substitution, our nucleophile is going to replace the sigma bond that was the alkyl halide bond. So in a substitution, our definition is going to be one sigma bond replaces another sigma bond. Likewise, in elimination, we have our electrophile being our alkyl halide, but notice over the reaction arrow, we now have the term base. Size is not going to be an important factor in understanding whether this reaction happens or not. Size is going to influence the product, but a base can be as big or as small as it needs to be in order to do this elimination reaction. Notice that what we have going on in this reaction, elimination by definition, is two sigma bonds are replaced. So they are broken, and what forms is a pi bond. Pi bond. So what we're noticing here is that these are the two sigma bonds. Not only is it that alkyl halide bond, the carbon that's sp3 hybridized to the halogen that's breaking, but also the hydrogen to carbon adjacent to that alkyl halide functional group is also breaking. And the pi bond exists right in between those two in the products. Typically, what we do with these alkyl halides is we start by denoting that the carbon with the halogen bond is called the alpha carbon. In both cases, the alpha carbon will be the one with a halogen attached to it. Anything adjacent next door is going to be the beta carbon. So an elimination is also known as a beta elimination. And so there is a pi bond existing in the product where the alkyl halide, the alpha carbon was, and the adjacent carbon, the beta carbon, as long as that beta carbon had a hydrogen. All right, so when the reagent can act as a nucleophile or a base, such as sodium hydroxide, we can see competing pathways. We will talk about this once we get through elimination reactions. So first, what we're going to focus on is just the concerted reactions of substitution, and then we'll do the concerted elimination reaction, and then we'll talk about competition. Just be aware that competition will take place. All right, so our substitution and elimination reactions. There are two main reasons why alkyl halides undergo these substitutions. We saw this a little bit already, but let's just go ahead and present a specific example here. There is an alkyl halide. This is what I'm going to call the alpha carbon. It is the one that is electron deficient, right? We have a delta minus and a delta plus appearing on that bond. Carbon alpha gets the actual delta plus, so it is the electrophile. It's making it susceptible to a nucleophilic attack. The halogen is what is acting as a leaving group. And for a substrate to undergo elimination or substitution reactions, it must possess a good leaving group. And what we mean by that is when our nucleophile or our base comes in to attack this electrophile, that bromine is going to be leaving as an anion. It will take with it, and we'll see this in just a second, it will take the electrons from that polar bond with it as it goes. So it will be what looks like a conjugate base. And so when we say something should be a good leaving group, we want to mirror that idea that it was a good conjugate base, like what we see here. Now, this chart is very, very important to remember and to understand. What you specifically need to understand is what makes a good leaving group. And that's something that we looked at with REO, understanding that a conjugate base was stabilized with atom size, with resonance, with induction, or with hybridization. What we see is our best leaving groups are the ones at this top of the chart. They came from the most reactive acids we have. And we do split it off right here, where we see a big jump in pKa from negative pKa's to positive pKa's. The negative pKa's, meaning very, very small numbers, are the most reactive. And so we'll look at all of these together and we'll be able to dive in. But again, think about REO and how you would have judged these conjugate bases as stable, coming from reactive acids. Why were they stable? Most often it's size or electronegativity, and then resonance. We see that with the tosyl group there, the sulfur with the oxygen negative charge. That has a lot of resonance there. Okay, so when we're looking at these SN2 reactions, what's really important to identify is the mechanism. The first step, or the first thing to identify, is what kind of a reaction do you have? We're going to first focus on the SN2 reaction. Now, the SN2 reaction is a substitution reaction that requires the loss of the leaving group and the nucleophilic attack happen at the same time. We will see both of these arrows, the nucleophilic attack with the loss of the halogen, the loss of the leaving group, happen concerted, meaning one step. And so with this concerted mechanism, it involves the bond breaking at the same time as the bond is forming. Namely, this first arrow of nucleophilic attack is the new bond forming between the carbon and the nucleophile. The second arrow that's happening there at the same time is the loss of the leaving group. The carbon to halogen bond is breaking. And so what we really want to be able to hone in on is a couple of these things in terms of what does SN2 stand for? How would we describe the rate law of this reaction? How would we describe the reaction coordinate diagram? So let's go ahead and do that now. SN2, notice that capital N is slightly subscript for us. Nucleophilic, involving a nucleophile. Substitution, And the 2 stands for bimolecular. And what we want to see with these bimolecular reactions is it is dependent on 2 molecules coming together. The rate determining step, the slow step, the only step here, this is concerted, is dependent on both the nucleophile and the electrophile. I'm going to abbreviate that nuke and elect. Now, why is this important to understand? Because in the lab, when we are doing these reactions, the rate law will tell us what happens to the rate when we increase or decrease the concentration. So if we doubled the nucleophile concentration, we double the rate. If we double the nucleophile concentration and the electrophile concentration, 2 times 2, 4, we quadruple the rate. So both the nucleophile and the electrophile are very important here. We need a small reactive nucleophile. We need an electrophile that has a good leaving group, and we'll also talk about a little bit more with that electrophile. Now, if the electrophile has a specific observed stereochemistry, it's R or S, the SN2 reaction being concerted is supported by our observations here. When we have our nucleophilic attack and the loss of the leaving group happening at the same time, what we observe in the lab is that if we had the S conformation of the chiral center, it will invert to the R conformation, and that's going to have to deal with the mechanism here. There's a concerted mechanism, meaning it's happening at the same time. How do we know? Because of our observations with these alkyl halides, specifically the ones that have stereochemistry. When we have a stereocenter, when we have a chiral carbon being our alpha carbon, there's alpha carbon with the leaving group, we always see an inversion of stereochemistry. If the starting material, the alpha carbon, was S, it becomes R in the product. If it started as R, it becomes S in the product. What does this tell us? That the nucleophile must be attacking from the back side of the reaction, the back side of the molecule, the back side or the opposite side of our carbon to halogen bond. We'll practice this a little bit more kinesthetically when we come into class, but what we want to be able to think about was just this idea of this blue highlighted as the sigma bond. Imagine where the antibonding orbitals were. The antibonding orbitals were on opposite sides. Now we cannot attack from the front side because if the nuke tried to attack here, it's going to be bumping into the bromine as the bromine tries to leave. That's steric hindrance. So we don't see the nucleophile attack from the front side. We only see the nucleophile attacking from the back side. Not only is it destabilizing that antibonding orbital when it does, it also removes that bromine in an open area. So there's limited steric hindrance of the nucleophile bumping in to our leaving group, which is beneficial. So one thing that we need to be able to identify here in this reaction is the transition state. What is happening in the transition state? And we said that the nucleophile's bond, we'll redraw it right here, the nucleophile's bond to the carbon, the alpha carbon, is forming at the same time as the bromine bond, the leaving group bond, is breaking. So a transition state is going to be able to show with dotted lines the transformation, what bonds are breaking, what bonds are forming, and don't forget you do have to show the rest of the molecule. I'll put on that wedged hydrogen, the dashed methyl, and the straight line ethyl there. Now, one other thing that's important in that transition state, sulfur started as a negative charge. As the bond is forming between sulfur and our alpha carbon, that actual negative charge starts to shift to a delta negative. And bromine, as he's gaining the electrons, starts to shift to an actual negative as well. So the backside attack is seen as in an observation of R versus S configuration, that inversion of stereochemistry. But what about that electrophile makes us think kinetics, right? What else about it? Well, we know we could have a methyl halide. That would be a carbon just attached with 3 hydrogens and the leaving group. We could have a primary alkyl halide. That is an alpha carbon with just 1 other carbon group. We could have a secondary alkyl halide. That would be an alpha carbon that has 2 other carbon groups. Or we could have a tertiary carbon for that alpha carbon with 3 other carbon groups. Now, what we don't observe is the tertiary. Not going to work. Why? Think about that. What happens as we increase the substitution around that alpha carbon? Methyls are the fastest. And as we go over here, we get slower. As we increase substitution, we increase steric hindrance around that alpha carbon. And the more steric hindrance, the higher the activation energy, and therefore the slower the reaction. Methyl alkyl halides are the fastest under SN2 conditions. Primaries are in the middle. Secondaries are slow. They don't like to do it, but they will. Tertiaries don't even try to do that backside attack. It's not going to happen. Now, when we talk about nucleophilicity, when we're talking about what makes a good nucleophile, what we really want to be able to identify here is that a strong nucleophile is going to be looked at as something that are anions, they are polarizable, and the solvent will affect their nucleophilicity. So these are all strong nucleophiles, anions. They are relatively small in terms of 1, 2, 3 atoms. In terms of those R groups, we'll talk about what makes the best size, but again, size is an important factor. Methyl can be the R group, ethyl can be the R group, but not anything past an ethoxide or a methoxide. We will see these weak nucleophiles later on. Just as a hint, they will be under our unimolecular reactions. So they can do substitution, they just aren't good at doing SN2 reactions because they're not strong enough. And the last thing that we want to say is the solvent. So we talk about the electrophile and the leaving group. We talk about the solvent, we talked about the nucleophile. Now let's talk about the 4th component, the solvent. We need polar aprotic solvents here. And the reason for that is because they are actually stabilizing the product of a concerted reaction. Polar protic solvents engage in hydrogen bonding. So notice they all have that polar proton, right? Polar hydrogen, polar protic solvents. And we will be able to see that they stabilize the anionic species. They stabilize nucleophiles, right? They stabilize the nucleophiles. We don't want our solvent to stabilize the nucleophile because we want the nucleophile to be reactive. So what an aprotic solvent does is actually destabilizes the nucleophile, makes it more reactive. And that is great because if we can destabilize our reactants, we lower the activation energy of our reaction, make it faster. And so we would always want to pair in an SN2 reaction, we would always want to pair our electrophile and nucleophile with a polar aprotic solvent, one that is polar but does not have a hydrogen that is polar.